Okay, for question 69, we're looking for integers that are upper and lower bounds for the real zeros of the polynomial. To determine this, we take a look back at the upper and lower bounds theorem. It says what we need to do is we need to divide by these integers, because that's what we're looking for. And we want to take a look at the quotient row, including the remainder. And if all of those entries are non-negative, then that's going to be an upper bound. If they alternate between non-positive and non-negative, that's going to be a lower bound. They could both be negative, they could both be positive, but let's just start at 1. So we have to add in a 0 for a placeholder. So we bring down the 1 and multiply. -2, 0, 0, and 4. So in this case, they're not all non-negative and they're not alternating. So then we'll go to 2. So in this case, we multiply. We have 2, so -1, -2 is -2. Again, they're not alternating. This was wrong, by the way. It was really bad math. So we have -2 here. And then this would be a -2, but we realize that we're not alternating, they're not all non-negative. So we can stop there. So then we get to 3. One, 3. Now this is 0. Multiply, this is 0, this is 0, this is 0, and this is 4. They're not alternating, but they're all non-negative. 0 is non-negative, so this must represent an upper bound. Okay, so we know the upper bound is positive, so the lower bound in this case, if it's an integer, must be negative. So we'll just start with -1. Okay, so -1 is a 0 in this case. Alternating maybe with the 0 of -1, we do want to check to make sure this is in fact a lower bound. So we'll keep moving here. -2, we have -5, this is going to be +10, -20, -16. Here they are in fact alternating, so this is a lower bound. So a lower bound of -2, an upper bound of 3. If we were to graph this, y equals x cubed minus 3x squared plus 4. What we see here is that our real zeros are 2 and -1, so in fact those were our upper bounds. So using the rational zero theorem in conjunction with Descartes' rule and the upper and lower bounds theorem, we can greatly reduce the number of possible guesses that we would have to make to get this down to a quadratic, so that we could then plug it into the quadratic formula to find the remaining zeros. And that's how you do solve question 69.